Jean-Paul, tu peux, tu peux,
morning. Good morning, everybody. Hello, ladies and gentlemen. Hello, I'm Michael Chegaspanyan, Leti's EVP and the chairman of this event. So first of all, I would like to thank all of you for attending this event, Leti Innovation Days for 2019. This year, the topic of the event is Deep Tech for Edge AI. So, for those who have already attended our workshop or the tutorial on artificial intelligence, I hope that you enjoy a lot the content. And if you need more information, please have a quick look on the program. Please, the program, yes. So we have got 5 more workshops on Thursday and Friday. So over the next 2-day plenary session, we will explore artificial intelligence with keynotes from speakers from academics, from industrials, panel discussion, startups, business meeting, an exhibition with plenty of live demos and networking opportunities during the lunch, during the coffee breaks. So now, for me, it's the time to introduce our latest CEO. So, Emmanuel Sabonadière.
Thank you so much, everyone. So, you know, I like these days. I love Leti, and what is close to my heart is really innovation. We are in the French Alps, and because the mountains are very high, we'll need to look over the horizon. And when we look over the horizon, what we have saw this last year is, in fact, edge artificial intelligence is becoming extremely big. Big for the industry, big for microelectronics, big for software, and big for the society. Our vision for artificial intelligence is, at the beginning, you need to create the model. And the model has to be created with a lot of data and a lot of power computing. Thus, the model has to be created into the cloud. And that's the reason why the first thing that has been to be established is having the model of AI into the cloud. But later on, you have to run what you have established as a model. And to run it, honestly speaking, there's 2 schools. The Chinese one and the American one, and the European one. The Chinese one and the American ones, we know it. Everything in the cloud. Data are free, they can use the data they want, and they will create artificial intelligence on top of what they can utilize, and they will monetize it in a certain way. Because this is the business model they have. In Europe, things are different. We have a regulation about the data privacy. We cannot turn around. We have it. We have to deal with that. And because of that, the second school, the European school, is in fact to move artificial intelligence toward local, toward a local chip. So you need either hardware and you need software to be local. And this is what we call edge AI. So edge AI will be a combination of trust in AI, so we have to demonstrate what could be done locally. The learning phase will be extremely local. We will not reinvent a model. We will complete the model with the local sensors, the local memories, the local computing. And, of course, we will need hardware. And this is the big deal. What kind of chip we have to invent for tomorrow for the AI hardware? We knew in the past GPU was used because it was a nice CMOS or a nice process we can use, GPU from NVIDIA. We knew that GraphCore has created a new dynamic with more calculation power, a little bit less with the memory and the learning phase in the memory. And probably in the future, we have to invent something much more balanced in between the computing part, the memory part, and the sensing part. And it could be either a chip, or it could be a microcontroller. And today, during this day, you will see ST showing what they have done with the microcontrollers or around the microcontrollers. And we will also have the discussion with the chips. So that's the kind of few things. I'm so glad that we can openly discuss, because it's probably a starting point of a long journey around this edge AI. There's a lot of collaboration ongoing around this edge AI. Some of them are taking them tactical. Some of them are really trustful in what has to be developed in edge AI. And overall, probably the next 3 to 5 years, when you will come in a year time from now here, innovation will be one step more around edge AI. So big story for us. Overall, in the Leti, we're also doing other things. You know, we have 4 main projects, or 4 main programs. The largest one is, of course, around edge AI, and that's the program for today. The second one is about quantum computing. So we believe for HPC, we have to be one step more, one step forward, and that's the reason why quantum is absolutely critical. And we have 2 cyber physical systems. One is around LiDAR and radars and multiple sensors. And the latest one is about digital 5G, because we know 5G is a big story, but digital and to filter and to able to transform data into information is something which is also critical. So that's the 4 main programs. But once again, having this day and these Leti days open on edge AI is very close to my heart, and I'm pretty sure that it will create a lot of innovations. So what I will do now, I will show you a little movie that has been done to give you a little bit how we see AI, edge AI, and the combination of all the sensors and the combination of all what is about. And after that, let's see what the keynotes will give us as a kind of new ideas about what could be invented. Thank you, and have a great Leti days.
Leti is a global leader in micro and nanotechnologies. Located in Grenoble, France, Leti's multidisciplinary teams tap into the most sophisticated machine ever created, the human body. Nature has gifted us with senses to interact with the surrounding environment, inspired by the human's extraordinary sensory systems, neural connections, and learning capacities. Leti is creating smart sensors and reconfigurable integrated circuits to provide optimized decision-making processes. Humans' performance comes from a smart mix of long and short connections. In the case of imminent danger, a nerve message reaches the spinal cord via the dorsal root of the spinal nerve, where it is then processed in the gray matter to mount a response. It is called the myotatic reflex. Similarly, bringing artificial intelligence to devices everywhere will require an extremely diverse range of new technological solutions involving the same smart mix of local and central processing. Leti has a strong expertise in FD-SOI CMOS, 3D integration, memories for neuromorphic and in-memory computing, photonics and imaging technologies. The Institute is developing highly miniaturized systems and highly sensitive technologies and components located as close as possible to the sensor. Together, these low-power technologies will address tomorrow's data deluge at the edge by making the data meaningful, secure, and actionable. Technologies will address the world's biggest societal challenges, fueling innovation in personalized healthcare, clean energy, e-mobility, and smart farming. Intelligent objects, from self-driving cars to robots, need to be equipped with multiple senses to scan and interpret their direct environments. LiDAR sensors, like our vision, identify and analyze areas of interest to map our surroundings. Leti's expertise in heterogeneous technologies mixing photonics and microelectronics enable low-cost mass production of LiDARs. Its sensor fusion solutions turn the myriad of incoming data into clear information for dedicated and intelligent action locally. These sensors will help turn everyday objects into smart objects, which will improve the lives of people, including people with disabilities. our world is entering a new era where artificial intelligence systems are shaping the future. To address the growing need for innovation in hardware and migrate AI to the edge versus the cloud, Leti is working on massive parallel, low power and low latency computation required to enable smart and low-cost devices that can learn on their own. In particular, Leti's designers are developing the third generation of spiking neural networks, strongly inspired by the brain, that fits on a chip for low power and local decision. Making embedded intelligence everywhere a reality in real time also requires connectivity with unprecedented speed performance and security. Another important requirement is to develop high bandwidth and ultra-low latency networks to support AI and machine learning at the edge, from baseband software, very high frequencies to smart antennas. Leti's teams have been pioneering 5G electronics and 5G field trials. They developed the required interfacing hardware technologies to tailor fully integrated 5G networks and beyond. From imagery through radio frequency and intensive computation, Leti builds on the scientific excellence of its teams to develop secure, sustainable, inexpensive, innovative solutions, and more important, help create a sustainable world.
So, I hope you enjoy a lot. So now it's time for me to introduce our host and presenter for this two-day plenary session, Bradley Stoke. Please, Brad.
Thank you, Michael. Thank you, Michael. Good morning, ladies and gentlemen, and welcome to the 2019 edition of Leti Innovation Days. This is, in fact, the 21st edition. So, just in the crowd, a quick question. Who is here for the first time? Stand up, please. Let's give them a big round of applause. And who has been here 2 to 4 times? Okay, stand up, please. And now, this is good for your movement, the old timers. Anybody who's been here 5 or more times, please stand up. You know that one of the very important aspects of Leti is the opportunity to meet other people, networking. So we have set up some business services so that you can meet other companies. It's right outside the canopy. If you've signed up for these events, you can go there at the prescribed times, just check your schedule. And if you have any questions, just go to the help desk. Also, downstairs, you have the Leti exhibition area. Make sure that you don't miss out on Leti's partners, some successful startups, and of course, Leti. It'll be running today from 12 to 6 p.m., and then all day tomorrow. Of course, the final point, Leti absolutely wants to thank all of its sponsors. Please give them a big round of applause. Deep tech for edge artificial intelligence. Deep tech is the key for edge artificial intelligence, and deep tech is at the heart of Leti's DNA. What we're going to give you in the next day and a half is an in-depth analysis of everything that artificial intelligence is impacting, both for the electronics industry and for the semiconductor industry. What I'm going to do now is jump into the subject by handing off to an expert on semiconductors. He's the CEO of Business Intelligence Strategies. Please join me in welcoming Dr. Handel Jones.
So I appreciate being here today. In terms of IBS, we've been in business about 30 years. We're based in Silicon Valley, so we track the activities in Silicon Valley very closely, and of course, activities in artificial intelligence. I do come to Europe fairly often. We're actually very impressed with some of the innovation in Europe. And again, I think what you have here in CEA-Leti is a great asset. In the past, in the US, we had Bell Labs, we had IBM Watson. Frankly, they're gone. So today you have IMEC, you have CEA-Leti, you have Fraunhofer. So you have actually a lot more innovation in many ways in Europe now than in the US. I also spend a lot of time in China. In fact, I go to China probably every 6 weeks. I've written 3 books on China, and the latest one was on artificial intelligence. And now we're actually doing an English version in terms of that book. So what is artificial intelligence? Well, artificial intelligence, by our definition, are capabilities that enhance the performance of machines, but also humans. And basically, it's based on the fact that you do have processing power, analytics, etc. But it will dramatically change many industries. Today, a lot of the activities in terms of AI is based on the cloud, but we also have AI on the edge. So the smartphone is an example of where you have the image enhancement for camera capabilities. So in terms of the impact of AI, as I said, is going to increase the intelligence of machines as well as humans. So we have this figure which shows you at the bottom, basically, the green, how human muscle power has enhanced over the last 5,000 years. So we have steady improvement, but nothing dramatic. So in the 1500s, 1600s, maybe 1800s, machine power came in. And suddenly we have this dramatic increase in capabilities. So now we have aircraft, we have the auto industry, we have a whole range of new industries that has come about because of electricity, because of machine power. So then you look at the growth of human intelligence, and that has improved over time. And of course, there's variation. Some people are very smart, and some people are not quite so smart. But again, it's a steady improvement. So then what we have is coming in, probably we have a real change in around 2016, the AI. And the growth in AI capabilities from an intelligence point of view is dramatic. And how do you get this? Basically through processors, through algorithms. And of course, if you look at the machine power, the muscle power of machines, that has created many new industries over a time frame of 200 years. But with artificial intelligence, we have the impact in 20 years. And the impact will be far greater than the impact on machines, on the muscle power of machines. So this maybe is a fairly simplistic figure, but this is what's happening in terms of society right now. So what you're going to have in terms of AI is basically, as I said, these enhancements in capability of smartphones, the picture-taking capabilities, smart cities, smart homes, etc. And then, of course, you're going to have you've got NB-IoT that provides low-level connectivity into the cloud. But 5G will be huge. And 5G basically is coming in quite rapidly. We have, frankly, Huawei a year and a half, 2 years ahead of what we have in Europe and the US. And the projection we have is that in China, by the end of this year, you'll have 150,000 to 200,000 5G base stations. Probably 50,000 are installed already. And this is sub 6 gigahertz. And the plan is 3 million in 3 years and 6 million in 5 years. So, of course, when you have the 5G infrastructure, basically, we don't think that millimeter wave will have the same benefits as the sub 6 gigahertz because of the short range. But once you have that infrastructure, of course, that can accelerate the adoption of AI. So what steps do you have in AI? The first steps that you have in AI is the automation of many tasks done by humans and also smart machines. So what this will mean is that probably in the next 20 years, 500 million to 1 billion workers in factories will be displaced by smart robots. You're going to have a similar disruption in terms of service industries. Again, displacement of people by smart robots and, of course, intelligence. And one example of that, of course, is now the 3D facial recognition, where basically you can buy goods by 3D facial recognition. Of course, that's going to also apply to entry into sporting events, financial transactions, etc. So that's going to basically displace a lot of what we have today. The second phase, which is going to be an important phase, is creation of new industries. So if we don't create new industries, we're going to have mass unemployment. And of course, the time frame that we have is 20 years. Whereas in the industrial age, we had 200 years. So now, what are going to be the new industries? So basically, I'll give you a couple of examples, but we think the medical field will be changed dramatically. And I'll go into more detail on that. Autonomous transportation, of course, is coming in. That's going to create, of course, new industries, but again, in many cases, you're not going to have the need for people. We also see the concept of digital twin coming in quite extensively. Right now, digital twin is applied to components for jet engines, also for jet engines. We think every semiconductor in future will also have a digital twin. And of course, the digital twin will be the hardware-based and also software. And the software will be algorithms, but also security. As you go into the AI arena, security will become increasingly important. We also do see augmented reality coming in, and of course, you're going to see that on smartphones in the near term, and also virtual reality. Virtual reality will allow me to be presenting to you right now by still being in California. So that's going to also change work habits because you can actually interact without the physical proximity. We do see gaming gaining significantly from AI, and of course, NVIDIA is pioneering gaming extensively. And of course, now we're going to go gaming in the cloud and content in the cloud, etc. So increased productivity of robots, drones, etc. Those are some of the industries. The third phase of AI is that all of us in this room will have what we call the virtual digital assistant. That is where the smartphone becomes a superphone. And the intelligence on the smartphone will be significantly higher for most tasks than is in the human brain. And so what the humans do in terms of thinking, analysis, etc., is going to change dramatically when you have the what we call the virtual digital twin. And again, that's 2025, 2030. So if you look at the smartphone today, basically you've got significant enhancements in terms of the throughput of processors, and now with the neural network cores, and of course you get 5 tops, 7 tops, etc. So these are some of the phases of AI, and of course I can go into them into a lot more detail, but again, we have limited time. So these phases are going to be fairly dramatic. And again, if we adopt AI and understand the implications, you can have huge benefits. If we don't, and if we don't have a plan for AI, if it's done sporadically and so on, it can actually cause mass unemployment. So the other part that we also see with AI is the link between AI and IoT. To date, IoT has not had significant growth, and part of the reason, of course, is there wasn't connectivity in the cloud, and there wasn't the ability to monetize IoT. We see that changing significantly. And of course, we see IoT in smart cities, in terms of smart agriculture, smart medicine. And again, where do we see the leadership? Right now, we see it in China. And of course, part of it is because of the installation of NB-IoT on a fairly broad scale. And of course, the commitment, top-level commitment to establish the infrastructure and then establishing things like smart cities. I think Wuxi is going to have 1 million sensors in the next year or so. A key part of IoT, though, is sensors. And in our opinion, sensors is the weak link in many areas of IoT. And of course, Europe, what we see in terms of CEA-Leti, what we see in IMEC, what we see in Fraunhofer, in Bosch, there's actually significant leadership in terms of sensors. And of course, it's important to maintain that leadership and then, of course, apply it to specific applications. So this is the market we're showing in terms of IoT and so on. So again, this is some of the ecosystem. So we do show significant growth. One of the areas that we think is going to have a huge impact in terms of people's lives and also the adoption of AI is what we call wearable IoT devices. The health industry is probably, at least in the US, 10 trillion and more. And the cost of health is increasing as population ages and so on. So in terms of the first product that we think has some significant impact is the Apple Watch 4, arrhythmia. But the real requirement is actually to be able to measure blood sugar content and blood analysis without drawing blood. So we hear that CEA-Leti has been doing some interesting stuff here. Manuel wouldn't tell me the details yet because he feels he's not ready. But this will have a major impact in terms of people's activities, people's diet. Your diet will be controlled in many ways, not by what you want to eat, but what the sensor will tell you should have to balance your nutrition. And in our assessment, this can actually increase longevity. It can increase productivity. And of course, the key requirement here, as I mentioned, is sensors. Also, you need low-power processors. You need long battery life. And then basically, you also need the analytics capabilities. So the concept of IoT is not just a microcontroller. It's not just a sensor. It's the whole application solution, which has all of those things in it, along with the algorithms. And in many cases, it's going to be the algorithms and the software that will be the differentiation. And of course, what you also need, as I said, tied into that is security. And then there has to be the database, the infrastructure to basically do the analysis. And again, I'm going to give you another example in terms of China. Today, China has 1 billion people in the database for 2D facial recognition. In the next 3 or 4 years, there'll be a database of 1 billion people with 3D facial recognition. And if you go into China, in the airport, they'll be able to take a picture of you, and in 5 minutes, they can find you wherever you are. So again, you have to build up the infrastructure, the database, to utilize AI as well as basically developing the pieces. So again, we think that the volume of the wearable devices can be hundreds of millions of units. And of course, when you do get this high volume like you have in smartphones, that's where you have the basis for investment and innovation and payback. So where are we in technology? FinFETs are in high volume production right now at 7 nanometers. We've done an analysis of the cost. The cost of 1 billion transistors at 7 nanometers is around 2 euros. 1 billion transistors. So transistors are cheap. So if you look at a complex chip from Apple, basically the cost is $15, $16 at the chip level. That's about 6 or 7 billion transistors. So transistors are cheap. Gate-all-around is coming in. Samsung basically expect to have production in 2021. We think there's a high probability of that. It'll initially be high cost, but we think gate-all-around with a nanosheet technology has a lifetime of 20, 30 years. It's going to obsolete FinFETs because you get analog RF functionality as well as the digital. So, but it will require 10 to 20, 12 to 20 layers of EUV, and there are still some issues in terms of EUV. What are the other technologies? CMOS, 28 nanometers is in high volume production. Basically, the lower limit is 22, maybe 20, but 20 was marginal. But now we're seeing FD-SOI coming in. We've been involved with FD-SOI for the last 10 years, but now we see significant design activities in FD-SOI. And of course, the key design activities right now is in RF, support of NB-IoT, 60 gigahertz in terms of connectivity, short-range connectivity, And of course, we've done significant cost analysis or extensive cost analysis of FD-SOI. So we have basically cost per transistor parity with 28 CMOS. We have also lower cost compared to FinFETs. So again, we see this now as coming in. And of course, FD-SOI was developed here at CEA-Leti. So we do think that you will have the migration in FD-SOI down to 12 and potentially to 10. The other areas that we do see very high growth is silicon carbide. And again, silicon carbide for electric vehicles. We see when we track the activities of Tesla, you can get maybe 15%, 20% longer range with silicon carbide than you can get with IGBT, silicon-based IGBT, and that, of course, saves your battery. The battery cost, battery weight, etc. So we do see silicon carbide growing quite rapidly, and the limitation will be capacity. Capacity for the substrates, because the crystals, the substrates, and so on. We also see gallium nitride coming in very rapidly. Also, if you look at the base stations being provided for 5G, they do have extensive use of gallium nitride. So again, specialty materials are going to become increasingly important, both in terms of the edge devices, but also in terms of the supporting infrastructure. So this is what we show in terms of the semiconductor market by product. I'm bringing this in because based on what we see as the issues between US and China, we don't think there's going to be a resolution in the next few days. We think the gap is too big. We do think that there will be the adding of additional tariffs on the $300 billion. The result is that the semiconductor market will decline almost $100 billion from 2018 to 2019. If there is a resolution in the next few days or the next few weeks, then we have to reverse our numbers. But right now, we're showing basically a decline of around 18%. Now, inside that, though, you have to look a bit deeper because DRAM is the biggest decline, and of course, that's a combination of reduction in gigabyte prices plus a slowing in gigabyte consumption. NAND is a significant decline also because of the gigabyte prices, but also across the other areas, we do see a significant decline. We originally had the smartphone market down 9.5%. Now we're looking probably closer to maybe 12%. And again, part of this is because of the dispute between the US and China. So that basically, the issue that also underlies that is that I talked earlier about the high growth of the 5G in China. If there is continued limitations in terms of supply to Huawei, and also maybe Trump will increase the penalties, then that could potentially force some slowing of the adoption of 5G in China. But our assessment is that even though the US activities can slow down China in the next 2 or 3 years, it actually will accelerate China long term. So, and it's also going to, it's going to have a significant negative impact, I said, on the US economy and also the semiconductor industry on a global basis. So what do we see in terms of AI? Basically, we see AI at the beginning of the adoption phase. So if you're basically running 100 meters, we're at the half-meter range. We have 99.5 or more to go. But we do see, as I said, initial adoption. Autonomous driving is AI. Logistics at Amazon is AI. 3D facial recognition is AI. Augmented reality is AI. The camera capabilities on your smartphone is AI. So we do see that accelerating, or we do see those adoption already. But the key issue in terms of that I'd like you to kind of think about is if you look at what muscle power has done in terms of machines, in terms of industries, as I said, like the aircraft industry, the automobile industry, all of these things have occurred over a 150-year time frame. New industry has been developed. AI, in terms of brain power, will actually have a bigger impact. And whereas the machine power eliminated some jobs, created new jobs, AI will also eliminate jobs. And we have to find ways to create new jobs. So that's going to be the challenge in terms of how does one adopt AI and optimize the value of AI so it doesn't become disruptive. So in terms of the key capabilities, processors are important. And we do see basically, I said, cost of silicon becoming low cost. Where we talked about the Apple processor costing maybe $15 or $16, the neural network chip inside that, which is 7 TOPS, costs 3 cents. So that, of course, can be at the edge. And, of course, the cost of the processor is quite low. So then the algorithms are going to be key. And, of course, then, as I said, the ability to provide not just the chips, but the full reference design, which has the algorithms, the processors, and the whole application solutions. So again, in terms of the other edge area, we do have autonomous transportation. That's an edge device. Today, we need 100 TOPS, but we also need 10 watts. So again, that will require significant enhancements in capabilities, et cetera. And then I think I'm getting time to. So again, smart cities, wearable devices, all these are excellent opportunities, but also involve challenges and also involve innovation. So thank you very much.
Thank you very much. So you've just been given the bird's eye view by Dr. Jones from International Business Strategies. Now we're going to move to the world of retail. The next speaker is a man who loves putting technology into people's lives to improve their lives. He is the co-founder and CTO of Bossa Nova Robotics. He has spent the last 20 years putting robots either into retail or into the households. He's built over 500,000 robotic toys, and now he's putting robots into stores so that they can navigate alongside shoppers. Please welcome Mr. Sarjun Skaff.
Thank you very much. Good morning. Thank you very much for having me. We're a startup company spun out of Carnegie Mellon University in Pittsburgh, Pennsylvania, in the US. And we are really, really honored to be invited in such a prestigious setting. So, Mikhail, thank you very much for inviting us here as a small startup. This is really big for us. And I also want to say to Emmanuel that as I was inspired by your opening remarks about the cloud being a US mindset and the edge being a European mindset. We build robots and AI, and in a sense, we span both worlds. So maybe without knowing it, we build a bridge between the two. So what I will tell you today is the story, is our story through the retail journey. And it may be a bit interesting that in today's world, when you are a robot, you're typically a self-driving car, and here we are doing robots in retail. Why? Well, if you actually take a close look at the way we're shopping, we are really being trained to want anything that we want, in any way that we want, at any time that we want. This is what e-commerce has trained us to do. And as a result, the entire retail industry is living a reinvention of itself to figure out how to service our new shopping needs. So you have online retail buying offline, you have offline retail buying e-commerce, and the brick-and-mortar stores, the retailers who have an established presence, are looking at their stores as a competitive advantage. They're asking themselves, how can I reinvent my store and use it as a distribution center and maybe win the last mile race? If I am close to populated areas, I could deliver the product faster, and this way I could fulfill the omni-channel experience. Well, for stores to be able to do that, number one, they need to know what's in the store so that they know what they can deliver to you. And number two, the stores are subject to a lot of pressure from e-commerce on pricing. And the only way for them to respond back is really with increasing efficiency. They need to reduce their costs and increase their sales. And in both cases, the way they can accomplish this is with data. They need to know what's inside their stores and what's on the shelf. It may be surprising that they don't really know what's in the store because the products get delivered from the back end and sold from the front end, so a simple subtraction should actually do it. In reality, the flow of products is so high, the store employees are always racing the clock and trying to put the right product on the right shelf, and as soon as they do, the shoppers come and disrupt it. So it's a real race, it's hard to keep clean, and the inventory is not very accurate. And that's exactly where we come in. So what we do is automate the data capture and analysis of on-shelf inventory. We really want to capture everything that's happening within the four walls of a store. And that is how we will empower the entire store ecosystem to really redesign the way a store is operated and also reimagine the way we're going to shop. We like to say that we scan every store, every product, every day to map the retail world. For that, we use both robotics and AI. To put it in numbers, when you go to shop in a store and you don't find your product, when you live in the US, that causes the retail market in the US to lose nearly $50 billion. If you don't know where the product is, you're leaving dissatisfied and the store is losing money. If the price is wrong, you're arguing at the POS and they need to write it down. So they are, when you tally them up, it's a massive, massive loss of revenue to the tune of more than $144 billion. And it's an obvious place where data is able to help. So for example, we don't know, we want to tell when the product is out of stock, we want to tell the location of products, and a great way of doing that is really to put eyes on the shelf. And the best way of doing that in large stores at scale is to mobilize cameras on autonomous robots. The next video will be of the robot in the store. It is not cleared for release, so perhaps the camera can pan away from it for a second. But I did want to give you a snapshot of what the robot looks like in the store. When the robot is not scanning, it is at its docking location recharging, and on a fixed schedule, multiple times a day, including during lunchtime and around shoppers, the robot goes on its own mission to scan the shelves. You can see here an optical stack with a battery of sensors. We actually have 15 cameras. We have 32 light spots. And as the robot rolls down the aisle, it is sweeping the shelves. And we capture supremely high-resolution images and 3D depth data of the shelf. The robots are essentially the indoor equivalent of a self-driving car. We're very cognizant of the world. We turn off the lights not to inconvenience shoppers. We're very good at going around obstacles. We've crossed thousands of kilometers without a single collision. We have a canopy of sensors around the robot that provides our safety. Here's a snapshot at what the data actually looks like. Somebody said that in IoT, the weak link is data. We're determined to make sure that that's not true for our case. We are here showing the 3D depth data. We have 6 time-of-flight cameras pointed at the shelf. We can see everything, including a store associate on a restocking cart. So we're very good at detecting and avoiding obstacles. And as I said, we have 15 cameras along the length of the optical stack. This is a zoomed-in portion of a single image. And look at the level of detail we can see. We can read all the content of a shelf label, the price tag, including decoding the barcode. The problem with so much data is that what do you do with it? That's the edge conversation. It's too much of it to send to the cloud. So what we do is we decode the barcode on this full resolution source image, but then we compress the images, we stitch them into this beautiful panorama that spans the length of the aisle. That panorama is sent to the cloud, and that's where we deploy our version of the cloud AI. This is best-in-class AI algorithms from Carnegie Mellon. We zoom in, we understand the shelf in its glorious detail. We don't leave anything to chance. So we detect every last product, we detect every last label, we understand the association between products and labels. So we try essentially to mimic a shopper. Just like us, when you go to buy something, you know what is the price, the algorithm knows as well. What that means is that we also know what item is missing. So we can detect an out of stock, read the barcode to know which one it is, and then alert the employee to restock. We also can localize everything, since the robot knows where it is at all times. It knows what it's looking at. And of course, we can read the price, and if it doesn't match what you will pay at the exit, we can go and correct the label. This data flows, this is a flow diagram about this data. It flows actually from the cloud through a number of systems that span the ecosystem of retail. On the left, you see the sales floor. We have our data delivered to the handheld of the store employee. We tell them what is an out of stock, not only in text, but also with images, so they can look at it and figure out what to pick and where to restock it. The PI data icon here is very important. The inventory system is supposed to track the product throughout their journey and figure out what's in the store. As it turns out, it has a hard time being accurate. So we help it increase the accuracy. For example, if it thinks that there are 2 products left on this shelf and we see that there are none, we can tell it to 0 the inventory. So we increase the accuracy of the inventory system. Our data is also sent to distribution centers. When we see the product missing on the shelf, it gets put on the truck and restocked the next morning. The planogram and the mod planning is interesting. If you know retail, you know that the way you present the products is very important to maximizing sales. How many facings, how many copies of the product, at what level. If it's at eye level, it's a premium location that sells more, etc. And so retailers spend a lot of energy and effort. It's actually a pretty good art into figuring out how to display products. And then as soon as those get sent to the store to be implemented, reality kicks in, and you cannot actually execute it exactly as it was supposed to be. So what we do is we scan the planogram, we figure out any discrepancies, and we feed that back to the store so they can go and fix the compliance issue. And the last one that has to do with location is the concept that if we know the location of every product, well, we can guide the shoppers to go and fill their basket in an optimal way. But also this applies to the store employee who is filling your online order. We can optimize their route, we can make them avoid out of stocks, we can even tell the shoppers that there is a replacement that they need to order if we already know that there is an out of stock at the time of order. In summary, what I'm saying is that we're allowing retail to completely change the way they operate their stores. They go from being schedule-driven, for example, on Tuesday, I'm going to look at the candy section, to becoming data-driven. Every morning, I'm going to look at the worst area of the store and go fix it in priority. It's a total mindset shift for the industry. Michael asked me to give a little bit more technical detail on the robot, this being a technical presentation. So here it is. We have, as I said, an optical stack on the side of the robot. The business end of that robot is the optical stack with 15 cameras, 32 light spots, 6 time-of-flight cameras. Those allow us to image without stopping and allow us to capture the resolution that we need to read the barcodes. We connect to the cloud over Wi-Fi, but we also have 4G in case of a failback, in case the Wi-Fi goes down. And speaking back to the edge, we actually have 3 server-grade computers inside the robot. It's essentially a data center on wheels. We do that because, of course, we need the autonomy piece, but also and mostly because we need to capture and process the data. So we have the capability to do it all on the robot in case there is a disruption in the communication to the cloud. We've been doing this since 2013. We've been running the robots around shoppers in complete safety. We've clocked over 24,000 kilometers, as I said, the indoor equivalent of a self-driving car. And importantly, we've captured more than 4 billion images. We have been in 50 Walmart stores for more than a year now. We just announced a deployment to 350 stores. And what this means is that we're capturing more and more data. And with AI, the more data, the better your algorithms. So it's a virtuous cycle that is making us ever more accurate. I was also asked to try to make an announcement if I can. Well, this will be the first time we're going to present our next generation robot. The current one I showed you is built mostly from off-the-shelf components for speed to market. But we've had 6 years of experience now that we have crystallized in our next generation robot. This one is completely custom built. So the optics are custom made. The compute is custom, and they're both designed to be best in class for data capture in store, as well as manufacturing simplicity and field replacement. In a sense, this is for us, it's the next step in edge computing, and it's also in taking the optic of the edge's edge. We want to do even more compute on the camera itself before it reaches the onboard computer. The robot is narrower, so we can penetrate more aisles, and importantly, it's lower cost. So better in every sense. With this robot, we're also going to do deeper analytics. Next year, we're going to be able to look through refrigerators and glass doors without any glare. We are going to cover the apparel section of the store with RFID, and we look down at produce and figure out the freshness and the availability of those as well. And I will end on the human factor section here. We put a lot of thought about what a robot should look like and behave when it has to live around people. And remember, this is store employees that are working alongside the robot, but also shoppers whom nobody warned about the robot and are seeing it for the very first time. This, by the way, makes us very, very excited to be able to deploy these robots and expose them to so many people. So we had to figure out what is the right balance between a robot that looks friendly enough not to scare shoppers away and purposeful enough not to look like an interactive device that people constantly interrupt. So you will not see any googly eyes or smiley face on our robot. However, it also will not be so overbearing and towering to scare you. So we tried to strike just the right balance. We did a lot of research in collaboration with human-computer interaction scientists at Carnegie Mellon. And the result is that, anecdotally, we're seeing that half the people ignore the robot, which greatly upset us at the beginning. But we, of course, learned to love those people. And there is obviously, as with any disruptive technology, a sliver of the population that's upset for any which reason with the robot. But we've been pleasantly surprised it's a very small minority of those. And they're largely worried about elements that are actually not true. This is the end of the presentation. I will leave you on a cute note. Even if adults actually ignore the robots, the kids are always there to warm our hearts and tell us we're doing something right. Thank you very much.
Thank you very much, Sarjun. So you've heard from the world of retail and a first application. As you've noticed on the screen, we're asking you once in a while what your opinion is on this or that question. Don't hesitate to reply. Now, we're going to take you to the world of healthcare and how AI can help human health. Our next speaker is Dr. Serafim Batsoglu. He is the Vice President of Applied and Computational Biology at Illumina. He's going to be speaking about the power of the genome and why genomics matter. Please give him a warm welcome.
All right. Thank you very much for inviting me. I'm very excited to talk to you today about the power of AI to help us understand the connection of the genome with human disease, genetic disease. So before I start, I want to see a round of hands. How many of us have had our genomes sequenced? Okay, maybe I see 1 out of 20 or 30 people. Well, why aren't we all sequenced? You see, I am at Illumina. Illumina is a company, I would say the leader in making machines that sequence genomes. And we have customers such as 23andMe and many more customers in the healthcare and across biotech. However, today, and it's funny that I would say that coming from Illumina, genomes are mostly useless. Okay, so we really don't understand more than a very tiny fraction of the contribution of the genome in human health and genetic disease. And this is something that we want to change. And to change that will require massive data as well as AI. As the genome becomes cheaper, and Illumina has been leading in making genome sequencing much more inexpensive, and as the applications of the genome become more and more true, we are going to hit a point where almost everyone will get sequenced, and many times in health. However, to get there, we really need to figure out how to connect data of genomes with rich longitudinal data in human health. So we see this happening over the next 10 years, as many datasets across the world are coming into fruition. And it's going to be a combination of large-scale data aggregation and AI. A big challenge is how to do this under privacy laws and policies, which are true in Europe, but also across the world. But there is ways to get around that in the sense of aggregated queries that do not expose the patient's data while getting enough information for AI to take place and basically connect the datasets. At Illumina, we have an AI group that focuses in understanding the connection of genomic variants, the differences in each of our genomes, and human health, and in particular genetic disease, starting from rare and severe genetic disorders all the way to common disease to make genomes useful for the majority of the population. So when we talk about human disease and their genetic causes, it is important to look at the spectrum of human disease. At one end of the spectrum, we have extremely severe genomic alterations that cause stillbirths or very severe pediatric genetic disorders. Those are typically monogenic, meaning that a single gene or a single locus or a single variant is the cause, and they are highly penetrant, meaning that if an individual has this variant, 100% they will exhibit that severe phenotype. At the other edge of the spectrum are genetic variants that are very mild or even beneficial. So they are related to basically human wellness, or at the intermediate level, we have variants of intermediate severity that cause more common oligogenic genetic disease. For an example of that, think of the many BRCA mutations that cause breast and other forms of cancer. Those types of mutations may sound extremely severe and bad to us, but really, for an evolutionary perspective, they only reduce the fitness of an individual by 1 or 2%, because an individual is able to be adult and have a progeny, have kids, before those diseases take effect. This is true for heart disease, this is true for diabetes, and for many other disorders. So when we talk about less severe oligogenic disorders, those are actually quite severe, quite important for us, but they are not as detrimental for the fitness of an individual as single monogenic, highly penetrant mutations. And those at the very far left are also ones that are extremely strongly selected against by evolution, which means that each mutation that has such an effect is only in a very small percentage of the individuals alive. So that's a powerful way of figuring it out. So so right now I would like to talk to you about an AI method that combines data from primate genomes, and I will explain how we do that, to understand mutations and their functional impact in human genes. So, within human genes, there is about 70 million possible mutations that could alter the sequence of a protein that basically is the product of a human gene. Of those 70 million mutations, many of them cause severe genetic disorders, such as those found in kids, pediatric disorders. So when a kid with a rare genetic disease is being sequenced, it is important to be able to understand which gene is severely disrupted and what is the gene causing the disease, and potentially which gene will be the one that should be targeted, if possible, to improve the condition of the patient. Unfortunately, of the 70 million variants, less than 1 in 1,000 are currently understood, meaning that they have been annotated in a database knowing whether each variant is benign, causing no problem, or pathogenic. Now, among the variants that are common in humans, so if we take this room and we sequence each of our genomes and we look at variants that are present in at least a few of us, each such variant is very unlikely to having zero chance of causing a severe genetic disease, because we are all healthy and you have that variant. The problem is that humans are very similar to each other. We passed through an evolutionary bottleneck about 50,000 or so years ago, where we were a very small population. So if we look at the room, each one of us is extremely similar to each other, much more so than other species are similar to each other. So in particular, if I sequence my genome and your genome, and we compare them, we will differ in about 1 in 1,000 positions. And if we sequence the genomes in the entire room, the differences keep repeating, so we actually don't get that much information. However, our close cousins, chimpanzees and other primates, are essentially evolution's laboratories where completely different sets of mutations have been tried and have been tested and have worked. And they don't cause genetic disease. And as we find in our analysis, when we looked at primate variants in the species sequence today, and we look at the databases of annotated variants as benign or pathogenic, most of the primate variants are benign. They don't cause a disease in human. However, still, the sequenced primates today are not enough to understand all of the human genes and their 70 million possible variants. So for that, we need AI. So what we did is we built a deep learning method combining primate variants and making the neural network recognize the patterns within proteins, the patterns within protein sequences that specify what type of location structurally in the motif of the protein looks like it can harbor a benign variant and what location may cause a very deleterious effect. To do that, we make the neural network learn what location in the protein is likely to harbor a variant in a primate versus what location is unlikely to harbor a variant in a primate. So basically, we have the primate variants being proxies for pathogenicity for the network to learn. And we found that this is extremely effective. So compared to previous state-of-the-art, and this is a very well-researched problem, we were able to dramatically reduce the error in automatically classifying variants as benign or pathogenic. So we were quite happy with that, but we can go further. First of all, we can use this type of filter, because this is really a neural network filter telling how likely a variant is to be pathogenic. We can use this filter to discover new disease genes. So together with collaborator Sek Kathiresan in his lab, who is one of the leading geneticists in cardiology at Harvard and Broad Institute, we looked at patients of cardiovascular disease and controls and asked for every gene how many rare variants that are called by primate AI pathogenic or likely pathogenic, how many of such rare variants are in the patients versus in the controls within that gene. And we find that if we filter with a primate AI tool, we find this gene in particular, the SERPIN-H1 gene, that has 18 variants in patients and only 1 in controls. So it looks like it is a gene that confers a high risk for early cardiovascular disease. And we found, for example, another gene that where the variants, curiously, are much more likely to hit the controls rather than the patients. And why is that? This looks like a gene that if you disrupt it, you actually reduce the chances of cardiovascular disease. So this is a very good target for therapeutic intervention and an example of what AI can do to help us give us hints of what to do in what drugs to develop. So because this is so effective as a method for understanding genetic causes of disease, we want to sequence many more primate genomes. And we really are in a race against time, because when you look at conservation efforts for primates, and you hear, oh, a species used to be likely extinct, but now the population has recovered. This is unfortunately not true for the genetic variation of the species, because if you had a family or a small number of families of that primate species, and they expanded, they don't have much genetic variation anymore. So we are in a race against time to sequence all the genetic variation present today in primates. So at Illumina, we are sponsoring a project we call the primate conservation, genomic conservation effort, and we basically want to sequence 10,000 primate individuals out of as many species as possible over the next 3 to 5 years. And we are collaborating globally to do this project. So we believe that every primate individual gives us as much information as 3,000 human genomes in understanding the causes of disease. And we believe that once we have 10,000 or so, we will annotate almost all of the variants in the human genes as benign or pathogenic and be able to understand the human genome. But the human gene variants are not the only ones causing disease. There is many other types of molecular variation that can cause disease. And another one that we have researched is splice sites. Basically, human genes encode proteins. And splice sites are the boundaries between the regions in the genome that encode the protein and the regions that do not. So a disruption in a splice site, even one base pair, can cause a completely different gene product or protein to be formed, so completely knocks out that gene. So those are very, very important variants, and they are actually causal for about 5% of the severe genetic disease. The only problem is that those variants are extremely difficult, have been to date extremely difficult to predict, because the connection between the genome and splicing was not well understood. The previous best method to date was only 18% accurate in predicting the location of splice variants. And this is a problem that has been, again, researched for the past 25 years or so. In fact, I worked on it also during my PhD. So at Illumina, we developed a method that just uses the human genome and its annotation of genes without data from populations or any extra data that we did not need to produce, but we built a deep neural network that takes the known splice sites as input and tries to predict whether a variant would cause a new splice site. As it turns out, our neural network was extremely accurate. In fact, I was surprised by how well it did. I was really proud of my team, I couldn't believe how well they did. So compared to the previous best method, which had 18% accuracy in top K, which means that you ask the method to find the top splice sites in a region and basically how many of them will be correct. So our method has 95% accuracy, so it is highly predictive. Using our method, we are now annotating the Genomics England data of 60,000 genetic disease patients, and we are finding many more diagnoses that were not previously possible. We also applied it in several cohorts, including with our close collaborators in UCSF, where we look at 4,000 autism patients and find 120 likely colossal variants. Over there, we also had peripheral blood for a number of these patients, and we find that our predictions are confirmed 80% of the time in peripheral blood, so that's a lower bar of the practical accuracy of the method. And this is an example of a patient that we diagnosed in the Genomes England cohort. This was a patient having basically multiple endocrine tumors. This is a disease that basically the patient gets tumors in multiple tissues of their body, and it is often caused by disruption of the MEN1 gene, which is basically multiple endocrine tumor suppressor gene. In this particular case, the clinical genomicists had found a mutation that was hereditary in one copy of the gene, but the disease only happens if you have two disrupted copies from both paternal and maternal. Our method found a splice site that knocks out the other copy and is the likely cause of this disease. So I'm going to stop in a minute. So in conclusion, with a combination of large-scale data aggregation and AI, we believe that we will be able to connect the phenotypic effect of every type of molecular function pertinent to the human genome with basically the effect on the patients. And this way, we will be able to make genomes more and more actionable. And as genomes become more useful, they will be more utilized in human health, and that will generate more data, which then, if we have methods that are able to aggregate them in a privacy-preserving way, that will lead to better AI and better understanding of the genome. So we want to get this pill winning, and this is one of the priorities of Illumina, as well as of the broad genomic community. So I wanted to thank my team and our multiple collaborators, and thank you for your attention.
Thank you. You've now heard about applications of AI in two very, very different fields. We're going to move on now to the technology that supports them. At this time, I'd like to introduce a new speaker, Patrick Gros, CEO of INRIA. He's going to share a point of view from a software point of view, and he's going to actually talk about the question of the latest advancements in deep learning. Patrick.
Hello. Okay, I hope the microphone works. So I will try to present AI from a software, an INRIA, and a Grenoble point of view. So I'm Patrick Gros. I'm not CEO. I have a CEO. I'm just director of the INRIA Research Center here in Grenoble. So first, a few words. What is INRIA? INRIA is a French National Research Institute for digital sciences. So we do mainly software, computer science, mathematics, control, robotics, but from a software point of view in all domains of computer science. So as it is applied, you know that computer science is everywhere, so we have application everywhere and links with most fields of economy. So what is AI from my point of view? First, AI is a major source of fake news, mainly because people think there is intelligence in AI, and this is wrong. There is no intelligence, only intelligence in the head of the developers. And telling the opposite is just a way to increase fear and reduce acceptability of these techniques in the population. But there's also some wise words, and I would like just to remind you that one of the best interviews about AI is that of Barack Obama to the magazine Wired, which was one of the best interviews about what is really AI and what is the future of AI. So AI is mainly a very large domain in computer science, ranging from natural language processing, speech recognition, vision, image interpretation, expert system, knowledge management, robotics, autonomous system, and so on and so on. It's very old. It started in the 50s. And so the question is, why is it just emerging now? Because even deep learning, this is based on convolutional neural networks, existed 20 years ago. And so the new thing is that if AI is not intelligence, mainly I would say that AI is brute force applied to big data. And then now we have the big data and we have the brute force. We did not have that 20 years ago. So, okay, a few words about deep learning. What's so new about deep learning? No, deep learning is just a new method of supervised learning. Supervised learning is just a technique where you try to discriminate between two classes of things, let's say two classes of images. And so this is a basic scheme where you have the positive example, you have negative examples, you represent these images like you use a discrete cosine transform or whatever transform you want. This is, in our community, we have Sift, Smurf, or many other descriptors to describe images. And you put that in a system that try to find the difference between the two classes. And when you have a query example, you just represent it with the same kind of representation, and the system will decide whether it's a positive or negative example. And the only difference with deep learning is that here you have no explicit representation, and you just rely on the system to learn the representation. And that's why we need, in fact, brute force, because computing automatically this representation from the data, the raw data, is extremely computer intensive. And so you need much more data, in fact, to be able to learn this representation, and much more computer power, in fact, to do this computation in a reasonable time. So in supervised learning, in fact, the human try to model the problem, and the computer try to model the solution. In deep learning, in fact, you just rely completely on the computer. So in practice, what you have is just, okay, you use mainly this convolutional neural networks, and you try at each level of the neural networks to compute, to learn, in fact, and to compute the good descriptors in order to discriminate between the different classes. And so you see here what is obtained, for example, to discriminate faces from other objects. And you can see that at the beginning, at the first level, you have very basic representation, which are quite close to DCT. But after, you have things like eyes, nose, mouth, and so on. And at the last level, you have something which is quite similar to faces. So what is it worth? So for image recognition, this is a kind of result we have. Now these systems are doing better than humans to recognize objects in images. But for action recognition, it does not work so well, because action is something much more complicated if you have a complex action. Image annotation, okay, now it works well, but for scene interpretation in general, the results are not so good. To learn correlation, that's very easy, but to learn causalities, this is very complex because a correlation is not a causality. So learning from 1 million images, extremely easy now, but learning from a few examples, this is very difficult because you have difficulty to learn the representation of the problem and to learn many things if you have very few examples. This is the difference between AI and a child. This is a child of 3-year-old. You show him a cat, he can recognize cat. AI system, you show him 20 million of images of cats. Okay, he can recognize cats. Okay. Autonomous driving, this is at level 2. Okay, you can do things with AI, but if you want to go to level 4 and 5, this is completely autonomous driving in unexpected contexts. Doesn't work so well. And so on and so on. This is to understand a sentence, that's fine. To answer one question, that's fine. For reasoning like expert in a small word, that's fine. To have weak specialized AI, that works. Proposing decision from data, no problem. On the other hand, understanding speech completely, okay, not done yet. Answering many questions in the discussion, that's more difficult. To reason with common sense, okay, AI has no common sense. Strong generalized AI does not exist. And explaining proposed decision is not done yet. What is a hot topic nowadays? Everybody is doing deep learning. What is really hot is generative adversarial networks. This is a way to make two networks work together, and this is mainly used for very impressive demonstration like generation of new data. This is, for example, used when you have one image and you want to have the same image with a style of a given painter or of a given style, or you want to transform things. And generative adversarial network is just, if you want to have a new Van Gogh, you just take a picture and you will have a Van Gogh with that. It's just, wow. And this is a real hot topic in the community for the moment because there was some application about painting and so on. Okay, that's fine, but what will be the real application, in fact, to regenerate data? I think there will be a lot of application, a lot of question about that. This is what is true data or not true data, because you will be able to generate whatever you want. What is going on in Grenoble? So the French government decided to create a few centers for artificial intelligence in France, trying to gather in a few places strong forces and many actors around this domain. And so 4 of these centers has been created. Donc, one in Grenoble, one in Paris, one in Toulouse, and one in Nice. And so in Grenoble, we have the MIAI project. This is Multidisciplinary Institute of Artificial Intelligence that was created, let's say, 2 months ago. So what it is, it's a consortium of 7 academic partners. Among them, there is Leti and CEA and INRIA, but also university and engineer school. We have lots of companies with us in the consortium, and we'll try to do different things. First, a lot of research about AI and basic techniques in AI, but also application to different fields and also to societal questions. We'll try to do also some training because in all companies and also in academy, we will need to more people train to this kind of techniques, and especially even managers in companies. We need managers who really understand what is AI and what we can do with that. And also we need citizens who are aware of what AI is or is not. And it's very important not to forget that if you want to have some acceptability of what we develop, we need also to train basic citizens. And we'll try to do innovation and innovating in a lot of fields like, of course, microelectronics, but energy, medtech, telecom, and so on. Some highlights about this project. The first one, which is really related to what is going on in Grenoble, is that we can go from HPC to Edge AI. This is, we have traditional computer scientists doing AI with a lot of resources and huge GPU servers to create lots of billions of images and so on. But I think we have also the chance in Grenoble to have people working in the industry of microelectronics and able to develop devices where we could embed part of the system. And especially if the learning phase is probably will stay on large servers because you cannot handle big data on small set. being able to do the recognition phase on a small device is probably a key point, especially in terms of privacy and keeping the personal data close to the user in order to, if you want to manage your own data, probably it's not possible if you just send them in the cloud and you just lose, in fact, the trace of, okay, what will happen to your data. So this is the first point. We have a real range from, okay, these huge systems down to very small devices, and we'll be able, I think, to develop this in Grenoble. Another point is we want to develop something which is called fair AI. If we want AI to be accepted, AI should be able to explain its decisions. And the techniques like neural networks are just unable to explain what they are doing. And especially what is very a key point is that there are some bias due to the learning data set used. And if you want to avoid discriminations, the system should really be able to explain what kind of data it uses, if there was some bias, how it takes its decision, because we'll have more and more decision taken. For example, just if you want to buy a house, to choose the client will be, okay, will be able to buy this house, there will be some AI, and if you want to have a mortgage, it will be some AI, and if you want, for many day-to-day, would say decision, there will be some AI. Respect privacy. This is something we are really aware in Europe due to the regulation of the European Union. Certify fairness. The problem of fairness is not just to say, okay, we did our best to have some fair system. We have to certify this. And we have to certify this formally. It's not a way of saying, okay, we worked a lot and we did many tests. This is not enough. We really need to certify AI, and this is very difficult. And after that, we have to develop ethical and legal frameworks, because it's not enough to let the companies say, okay, my AI is good. We have to have regulations. But if we want the companies to be able to develop such systems, we need to develop what we call value-based design techniques, which allows them to introduce these values directly in their development process. And this is probably also a key point from a computer science point of view, that it's not enough to say, okay, we'll certify after that if we don't give the company, we don't provide the company a way, in fact, to provide the AI we want. So we have really to develop new technique of development which introduce ethic point of view directly from the beginning. After that, in terms of application domain, clearly in Grenoble, there's a lot of things going on medicine, about health trajectory, about patient empowerment, about medtech and so on, because there's, I think, lots of companies from big one to small one working in this domain. And also there's a lot of works that will be done in this institute about environmental monitoring. We are just in an environment, this is with a lot of mountain around, which is very sensitive to the temperature, and with higher and higher temperature, we'll have lots of catastrophic events around, because the ice melt, because where we could go climbing, it's not possible anymore, and there is problem of water and so on. And so we have very good colleagues in environmental sciences at Grenoble University, and we really want to focus and work with them to develop new techniques to try to monitor and, if possible, predict and avoid these catastrophic events. Thank you very much.
Thank you, Patrick. We're now going to be moving from software to hardware. Slowly but surely, AI is migrating to the edge. The cloud is not going to disappear, but more and more calculations will be made locally on local devices. So at this time, 4 experts from Leti are going to share their 10-year vision with us and reveal some upcoming opportunities. Let's give them a big, warm welcome. Is everyone happy? Yeah? Good. Our experts are coming. All good? Sorry.
À quoi ça ressemble selon toi, Jarvis? Assez semblable à un atome, auquel cas le noyau serait juste là. Accentue l'unisphère.
Veuillez patienter pendant l'initialisation de votre OS personnalisé.
Je suis là.
Oh. Bonjour.
Bonjour. Qu'est-ce qui va pas?
Qu'est-ce qui te dit que ça va pas?
Je sais pas. Je le sais, c'est tout.
This artificial intelligence? Really? No way. And if ever it comes to that, there is still a lot of work to do. Anyway, we are on our way toward artificial intelligence. Besides being capable of high-performance computation, machines today and in the future will be able to learn, to classify data, to analyze situations, to understand context with a high accuracy and relevance. Artificial intelligence will be more and more part of our lives, to the point where humans and machines will intimately cooperate in the continuity of what we do every day with our computer or our smartphone. To obtain a fluid interface between humans and machines, researchers are focusing on new algorithms that can optimize data treatment performance. But specific hardware solutions will be needed if we want to massively deploy artificial intelligence all the way from cloud to embedded system. That is Edge AI. For us at Leti, Edge AI is bringing together learning and decision-making, sensors and actuators. The common point of all these Edge AI systems is that they must be frugal in energy consumption. To meet this energy challenge, and more generally speaking, the challenges of Edge AI, Leti is developing technological solutions through new hardware paradigms that will twist the way algorithms are made. Today in healthcare, artificial intelligence helps doctors on a daily basis to improve their diagnosis. But tomorrow, micro robots in our bodies will allow them to analyze a pathology at the very place where it is the most relevant. Thanks to Edge AI, these micro robots will locate themselves, analyze their environment, and deliver drugs to the right place. By 2050, 60% of the world GDP will be produced by 750 metropolitan areas. It will be necessary to reinvent the mobility of people and goods in order to limit pollution and save resources. Today, taxi robots are a reality in China and in the US. To generalize their uses, these machines will have to learn local habits to behave like Parisian, Napolitani, or Mumbai drivers. This will be possible thanks to Edge AI. We believe that in 10 years' time, Edge AI will be present in robots, communication tools, transportations, at home, and finally in every object we carry every day. Indeed, some AI uses will require two things. Controlled reaction. Do you imagine a vehicle waiting for a result from the cloud 1,000 kilometers away to brake? Security, I mean in terms of privacy and trust. Who would admit their personal health data to be transmitted to their insurance company? In order for this artificial intelligence use to be as close as possible to the place where data or decisions are produced, there are many hurdles to be overcome. As with any problem related to embedded systems, we need to compromise between complexity of the problem to be addressed and available energy consumption. For the needs of Edge AI, two areas of optimization emerge. Reduce the energy per operation, reduce the number of operations for the same function. To explain these needs in detail, please first welcome our first speaker, Frederick Heitzmann.
Thank you, Léa. Can you hear me? Yeah, perfect. Good morning, everyone. So, yeah, the problem of designing an AI system is so broad. Allow me to focus on one part of the problem, which is how do we reduce the energy consumption for each operation. Today, when you bring the data from a memory to a processor, it costs actually 100 or 1,000 times more energy to bring the data than actually processing the data. So when it comes to artificial neural networks, the problem is how are we going to bring much memory and many processing elements. So definitely we want to reduce the data movement, and that's what I am going to talk about. Allow me to give some detail to you about 4 main ideas about how we're going to reduce this data movement. Idea number 1, let's bring together the memory layers and the processing layers. Thanks to 3D integration, we're able to stack them all together in a single chip. So instead of having these 2 components separated by millimeters, we get to the micrometer scale. Having shorter wires means having smaller electric capacitance, and smaller capacitance means less energy. So we can even go further by integrating several processing layers or several memory layers altogether. The second idea is, what if we could even prevent the data from moving at all? We've been developing emerging technology for non-volatile memory. Non-volatile means you load the data in your system and they will stick forever, just like your USB drive, basically. The very big difference is that compared to a USB drive, this non-volatile memory, we can integrate them in a very dense manner and we can stack them onto the processing element. These two ideas work at chip level. We can go a bit further by getting into fine grain. So third idea is, let's take the processing elements and let's take them individually and let's merge them into the memory. We've been designing technologies like computational SRAM. The idea is, let's start with the conventional SRAM memory and let's put operators like addition, subtraction, Boolean logic into the memory component. The area cost is pretty negligible, and you start getting the idea. The memory remains, the data remains in the memory, and they do not move across the whole system. We can go into finer grain integration by designing what we call a cube of several layers with processing element and memory element all intertwined together. But before going to my fourth secret idea, let's think about how the biological brain works. If we look at it, there is no such thing as memory storage on one side and processing elements on the other side. Each individual neuron is actually capable to doing both, memorization and computation. So we're going to try to do the same with our own technologies. So let's use resistive memories altogether with specific design technologies. And we're going to use what we call analog computing to be able to do this individual operation like the one we need in artificial neural networks. So basically, the idea is, let's do the multiplication with resistors and let's do the additions by connecting wires. So that's pretty difficult to do more integrated like that. If you want to have a look at how it works, I invite you to go to the exhibition booth. We've developed a circuit named Spirit, which implements this concept. And there is a live demo. You can even play with it. So I hope I will see you there.
So thank you, Frederic. If I understood correctly, the Credo don't move the data will be the major challenge why AI will start using more and more data? Easy?
Yes, you get it. Don't move the data ever.
Okay, now another axis of innovations is to reduce the number of operations for the same function in order to lower the energy consumptions. To let us explain that, François Perruchot, the stage is yours.
So thank you. Yes, so we can try to reduce the number of operations and their complexity. As you mentioned, many people are working on new neural network design to try to do this. But there is another way to look at the problem. We can use the data. It's especially true for ultra-low power applications with sensors. We can use sensors to provide better data. Today, it's possible to run a basic neural network to do some image classification on a low-cost microcontroller. Okay, it's just 10 classes. It's low-resolution images, but it's quite already a challenging task. It takes 5 milliwatts to a specialized microcontroller to do this at 10 frames per second. Not too bad. The problem is that the accuracy is only 80%. So Not so good when you know that to increase the accuracy, you will probably need to increase exponentially the number of operations. But look, it takes only 10 microwatt to the sensor to provide the data. So 5 milliwatt, 10 microwatt. I'm sure we can do better. We can propose a better optimization of the system. Let's have a look at the process pipeline and try to find the bottleneck. It starts with some raw signal acquisition by the sensors. It ends usually with classification in the neural network. You can try to do direct classification using your raw signal, but it's very difficult to get good results. So what people do is that they put in between what is called feature extraction. Feature extraction is key. This is where you define the type of abstraction that you will use for your classification. If you can manage to do this in your neural network, then it can be very good in terms of accuracy, because you can learn this feature extraction from your data, like you do for the classification. Good for accuracy, but very bad for the number of operations. It's why today, for most of the ultra-low power applications, feature extraction is still done by some classical, I would say, digital processing using handcrafted mathematical formula. It can do the job, but you lose the power of feature extraction learning. And we think it does matter. So, how can we combine ultra-low power and feature extraction learning? We propose at Leti to use a specific type of neural network. They are called spiking neural network. Spiking because the information is encoded as a train of pulses. It is a very good way to reduce the number of operations, because the neurons process the spikes only when they arrive, and they emit new ones only when there is relevant information to transmit. It's called event-driven processing. We also propose to look at what image sensors are doing. It means using multiple but smaller sensors to provide basic data but in parallel. Neural networks are designed to process parallel data. It means also being able to fabricate this sensor with the same technology on the same die to reduce the cost. So, to summarize, we need to look at the full process pipeline. Quality of feature extraction is key, and the capability to learn this feature extraction. And we believe that spiking neural network combined with sensors array are the next move to be able to increase the accuracy for ultra-low power, keeping neural network small enough.
Thank you, François, for sharing with us this vision on sensors. Finally, all this has to be put into silicon wafers. And here too, we need deep technological innovations. So please welcome our last speaker, Emily Vyasnov.
Thank you, Leah, for the kind introduction. Can you hear me? Yes? Okay. So as Frédéric and François mentioned, Edge AI systems will be optimized along two directions: reduce data movement and compute only optimized data. So the first trend is to reduce data movement by bringing closer computing chips and memory chips. How does this no data movement concept translate in terms of technological challenges and specifically hardware? First, we need embedded processors that are highly energy efficient while remaining super performing. Fully depleted SOI, developed at Leti, is a key technology for Edge AI systems. It relies on adding a thin layer of insulating silicon oxide within standard bulk transistors. And this innovation confers transistors to perform quickly and energy efficiently while pursuing the challenge of miniaturization down to 10 nanometer node and even below. 28 FD-SOI has already proven to be ultra-low power in many products, but also in neuromorphic circuits. Samurai is one of these circuits that we designed at Leti, where we use the low voltage capability of FD-SOI together with the back bias in order to achieve up to 2 tera operation per watt, which is twice as efficient as similar non-FD-SOI embedded processors. Second, Edge AI system will require memory, and especially ultra-small memory points able to store synaptic weights. This means that we have to find materials able to store value in ultra-small volume while being compatible with ultra-low voltage of CMOS. And these memory points have also to keep the value even in off mode. At Leti, we are developing this non-volatile memory, mainly resistive random access memory, like PCRAM, OXRAM, and FIRAM. These materials offer non-volatility, with up to 10 to the 9 retention capability when they are read, and up to 10 to the 6 when they are cycled. As Frédéric mentioned, once having ultra-low power embedded processors, together with ultra-small non-volatile memory, what about bringing both closer in order to save energy and to save data movement? For this purpose, at Leti, we are developing a set of 3D technologies, from wafer to die to wafers, with interconnection density ranging from 10 to the 3 interconnection for each square millimeter up to 10 to the 5th. And with these 3D technologies, we are able to mimic the dense interconnections that we just, all of us, have in our brain. With these 3D technologies, it's possible to bring computing chips as well as memory chips close together through a passive or even an active interposer. But these technologies also allow to partition neuromorphic chips in elementary cells and then reassemble them to build a wide family of circuits, just like Legos. If we go even further, we could not only merge computing and memory, but computing, memory, and sensors or actuators. This allows data optimization close to sensors and decision close to actuators. What kind of technologies do we need to do this? 3D sequential, called CoolCube and designed at Leti, is one of the first key technological bricks to integrate processing units close to sensors. With this technology, we can slice in different horizontal layers computing chips, circuits, and stack them onto sensors. And with up to 10 to the 8 interconnections per square millimeter, CoolCube will easily follow the trend of having dense arrays of sensors. What about memory? Ultra-low volume memory can also be achieved by using multi-level memories. This means that RAM will not only store 2 values in each memory point, but several values corresponding to several resistivity states. By using this concept, our team have designed a circuit where each memory point stores up to 5 different values. This concept multiplies by a factor of 2.5 the amount of data that we can store in one single circuit surface. If we go even further, we are also designing a new version of our neuromorphic OXRAM-based circuit called Spirit, and that Frédéric already mentioned, where we use this multi-level concept, and each memory point will be able to encode 4 bits, meaning up to 16 different values in one memory point. Finally, If we want to fully mimic our body, we need dense interconnections, but also heterogeneous. By using wafer-to-wafer, we have been able to build an ultra-fast smart imager called Retina, which is able to record more than 5,000 frames per second. If we want even more heterogeneity, we could use die-to-wafer to stack, for instance, a piezoelectric chip on top of a CMOS for immediate data treatment. But we could also stack a combo of sensors or actuators on top of CMOS. Finally, if we combine all these 3D technologies, wafer-to-wafers, die-to-wafer, and CoolCube, we could really build this dense and efficient 3D edge AI system, which will embed all the functions from memory, computing, and up to sensing. All in all, in the end, what matters is our ability to tackle these new AI architecture systems from the choice of the materials up to the component level and onto the system design. And because at Leti we are covering the whole value chain, we can help you find your way in this sea of technologies. You will get the technological implementation that is best suited to your specific edge AI system, and that is optimized both from a data point of view as well as from an energy point of view.
Thank you, Emily, for this overview on ongoing developments. Before we end this latest session, and just to convince you, if ever, that we will need edge AI in the future, let's have a short trip to a place where cloud computing would be hardly operational.
Top. Allumage des deux API, décollage, Ariane, VA 247.
Hey, for you guys, take one moment, look at the overhead windows on Discovery.
Okay, Ronnie, I'm ready to start motion station forward. We will let you know when we think that the NTA is out of the truss so you can relax a little bit with it.
Okay. Mike, in the meantime, you have a go to pull the NTA out.
So, thank you for giving us your attention while we shared with you the Leti vision on edge AI.
So a big thank you to Leti for sharing their vision with us. Then the question arises, given all these trends, what will the impact on the semiconductor industry be? To learn more, we're going to hear from ST Microelectronics, a world leader in semiconductor solutions. So at this time, please give a warm welcome to Claude Dardan, President of the Semiconductors and Microprocessors Group. Thank you.
Thank you. Good morning, everyone. So I will back to Earth now. So I will tell you where we stand, because we are all talking about AI. And in fact, while we try to be very pragmatic to bring solutions immediately for our customers. First of all, we have seen in the past few years, the world is moving to digital, is more and more digitalized, and we see a lot of smart objects proliferating everywhere. So, in fact, in all those smart objects, we see microcontroller as acting as a brain of each application. In fact, the brain of those applications being a microcontroller, we have had this idea in order to try to promote AI on those platforms. Second point, we see today the world becoming more connected. We see a lot of activities on IoT today. We are in the phase 1 of the IoT deployment. Phase 2 will come with a 5G deployment, of course, because as soon as 5G will be deployed, we are going to have the capability to have a lot of nodes per square kilometers. So this will give us a lot of opportunities to distribute and to have a pervasion of smart objects everywhere, connected or not. So, in fact, what we have done the past few years is to develop and to proliferate our microcontroller, and the question for us was, what can we do in order to address AI? So first of all, we said we want to be leader in embedded processing, and we must capitalize on the job we have done the past 10 years. Just to make a long story short, we were number 12 suppliers 10 years ago, and we are number 2 worldwide supplier last year, and we grew a lot the past few years. You can see that here. We had installed a customer base with where we have more than 60,000 customers identified worldwide using our chip. We have more than 1,000 products available. We have shipped, as of today, more than 4 billion units worldwide, and every month we are shipping more than 120 million units right now. And of course, we are capitalizing on the advanced technology we have on 40 nanometers. So we have a very, very nice foundation in order to prepare the future on AI. Last but not least, we were not addressing until now a key part of the embedded processing market, which is the standalone microprocessor. This is done since this year. We have been able to bring on the market our first microprocessor product, which is in the continuity with what we do on microcontroller, bringing more computing power, bringing more performances with a multi-core approach, but without any internal non-volatile memories. So we have everything in place now. How the market will move, where we are going with this market on embedded processing. So we have seen previously some very nice concept, but today that's reality. Okay, the microcontroller are classical MCU, embedding NVM and a lot of computing power, plus microprocessor. What do we see? We see, first of all, more connectivity coming. I told you today we have version of MCU with the BLE, Wi-Fi, threads, narrowband IoT for IoT, etc. So we have a lot of options in terms of connectivity. If you want to go direct to the cloud, you have narrowband IoT. If you want to pass via a gateway, you go Wi-Fi. So being a more connected world, in a more connected world, we must bring more security. Security is a key point to succeed. If no security, there will be no connectivity and no IoT. So in parallel with what we do in connectivity, we are working a lot on security, which is one of the strengths we have since we are in this domain for 25 years. And of course, last but not least, many applications will have to have embedded AI capabilities. That's the next point. And this is what we consider at the edge. Here I show you some application example, quick overview of what we can do, which type of market and which type of application we can cover. But this is just a small overview. This market is going to be highly fragmented. There will be 1,000 million of applications everywhere, millions of customers everywhere. We must be ready. We are talking here about mass market. So for us, distributed AI today, in 2019, means we are talking about various options. Endpoint, which are nodes or smart objects, standalone, okay, objects which are not going to be connected to any gateway or to any cloud, but will be a fully autonomous type application. Here we are talking about sensing, we are talking about need for data privacy, bandwidth, restriction of consumption. We are talking about real time, which is a key point. Okay, if you have all AI algorithms running on your platform, there is no issue linked to the connectivity, as the real time is there. Second point, second level, is when you have AI embedded in gateway, industrial or home type market. So here we have more capabilities in terms of connectivity to the cloud, but it's not obvious. Very often, your application will run at the endpoint we'll have a connection to gateway, period. So here, when we are talking about addressing the edge, we are talking about those 2 points. So what is a smart object? It's very, very general definition. A smart object for us is, of course, you have a sensor actuator, which is normal. Then you have to bring the brain of the application to drive your sensor actuator, computing data. And then, based on the type of application you have, you are going to bring some level of security and also some connectivity, depending on your application. But in all the cases, there will be the brain, which will be the microcontroller. And of course, what we try to do today is to add AI capabilities on this platform. So, acting that way, you see the way we are going to insert our product within the model. So, at the edge, endpoint, there will be the full line of microcontroller STM32, which are going to perform processing, actuating, connectivity, security, plus sensing coming from other divisions of ST. So we have all the platform. Gateway, there will be more sophisticated computing power. In that case, we are going to talk about advanced MCU and also microprocessor, performing processing, connectivity, and security. So you see security everywhere, connectivity everywhere, but limited versus the type of application you are targeting. And of course, we still have the option to be connected to the cloud. Why we want to go that way? Because we see the market moving that way. We see today machine learning coming on the market. 2 years ago, nobody was talking about machine learning. Now we see in the analysis presented by AspenCore recently, in fact, that 15% of the people will work on machine learning in their future design. From 0 to 15 within 1 year means they have started. The kickoff is there. Second point, when you see the dynamic by application, of course, the leadership is done on embedded vision, but we see machine learning model, also AI cognitive capabilities are also high growth driver. So we see today those markets growing fast, and those markets correspond with what we do with MCU. Therefore, we are in the right spot, and we want to move on faster. Which are the AI applications running on STM32 platform? I think that we can differentiate those applications in 3 categories. Low end, when you are talking about 10 million operations per second, where you do sensor analysis, activity recognition, motion sensor, stress analysis, etc. A standalone MCU will have, as today, enough computing power in order to perform your application. Medium, when you start to do audio identification, speech recognition, object detection, where you have a more advanced MCU or specific MPU or MCU embedding some accelerator. And high-end application, where you have a lot of activities, speech synthesis, etc., requiring operation at 1 to 2 tera operations per second. So today, with our MCU platform, we can cover, I will say, low and medium type application. And when we want to cover more sophisticated application, we are bringing devices embedding hardware accelerator to complete the job done by the STM32. You see here under some example today of application running in production, where we have been able to develop with our customers, those platforms. Sagemcom, they have done a system for predictive maintenance based on a vibration analysis, AI capabilities done with a partner, and this in production right now running at Sagemcom. Then you have what we call NNF, which is a Japanese company, where we are able to track, to recognize motion. And in fact, whatever you do, we are able to recognize the motion you are performing. Open MV Machine is a very low-end vision camera, easy to implement, able to classify up to 30 objects differently. Of course, 30 objects is not a lot. If you want to do more, you can move with a microprocessor platform where you have the capabilities to classify 1,000 objects. So all those demonstrations are available in this showroom of Leti today. And you will see that today customers are moving on with a lot of AI capabilities embedded in our platform. So what do we do to help our customers to deploy AI on their application? First of all, we are not covering the neural network trends model. Okay? People are using a framework available on the market, and they are able to develop their own neural network model. What do? We are able to provide with the Cube AI the software able to do the portage between the neural network model to executable code by STM32. Okay? This, of course, is a very sophisticated software piece, but this is what we need in order to give the capability to our customer to run their application on our platform. So the key point here is to be sure that we are going to maintain Cube AI at the right level. Today we see framework makers bringing new features permanently, and permanently we have to adapt our Cube AI to the new feature provided by those companies making frameworks. But it works. Today, I can tell you that many people are using this STM32 Cube AI in order to develop their own application. So the critical point for us, in fact, I see that here. You can see that here we have a training network model. We bring that on STM32 Cube AI, and we have everything in order to move on and to deploy your deep learning design frameworks. So in terms of equipment provided to our customers, of course, Cube AI is a main tool. It's a software tool available today in a permanent evolution, accessible free of charge to all customers via the web. And this is not enough. If you are giving this tool to customers which have no knowledge on AI, it will be difficult for them to start their application. What we do, we are able to provide a lot of software examples to our customer for quick prototyping in terms of audio and motion packs. So in order to help them to develop their application. They can reuse what we are giving them in their application, then they're able to deploy without knowing how to train a neural network. We make it very, very easy to access. Second point, we have also a very, very large STM32 community, having 60,000 customers worldwide. We have a lot of customers sharing their experience working on our platform. And of course, all those people who started with the Cube AI are extremely, I will say, are ready in order to communicate their experience worldwide. So people have access to this STM32 community focusing on AI. And last but not least, we have a lot of partners. Partners which are working with us, bringing added value on our platform, and we are giving access to those partners to our customers. So in fact, we have Cube AI plus a lot of tools to support the deployment of AI application on our platform. So the roadmap I just shared with you just before the evolution of this roadmap on Cube AI, you see TensorFlow. TensorFlow, for example, they came with a TensorFlow Lite in order to address the microcontroller market. In fact, our priority was to adapt ourselves in order to work with TensorFlow Lite. And we are going to see also some, I will say, it will be Amazon plus Google working together to propose Onyx software in order to establish a standard in terms of frameworks. We are on the top of all those tools in order to be sure that we are going to be well synchronized with all the frameworks available brought on the market. That's a key point to succeed. And finally, what is the result of this deployment? In fact, the result is today we have, since 2008 until 2019, this year, we have brought almost 70 series of product STM32, entry level to very high computing with a lot of memory, with a lot of peripheral, with a lot of analog function. I mean, a lot of differentiation. And also, we brought in Q1 this year the first microprocessor. You see here, you are able to run even products which are 10 years old to run machine learning or deep learning on those platforms. Of course, when you want to run deep learning on a processor which doesn't have the right computing power, you go nowhere. In that case, you go to machine learning. But at least on all half of the devices with a sophisticated computing power, based on Cortex-M4 and above, we are able to run deep learning AI capabilities without any additional hardware platform, which is a key point. So today, you have all those people using this product line. Using CubeAI, they're able to deploy their application on microcontroller in a very easy way. It was our goal. But we are not going to remain that way. In fact, because we cannot remain with the current microcontroller, because AI evolution is there. We need more computing power. We need to go deeply, providing more advanced features adapted to AI capabilities. Therefore, we are going to develop a lot of new products. Here you have the 4 points, which are just summarizing our strategy. First of all, with the CubeAI software available, we should see a lot of new capability, a new opportunity for customers to address a new market with the same platform. First point. Second point, AI capabilities will provide a lot of opportunities for new application. And we are able to provide also a lot of hardware platform in order to help customers developing their application. Third point, application running, AI application running on microprocessor today are costly. And today, with advanced microcontroller, we are able to substitute the microprocessor with the most advanced MCU, which is far less costly. In other words, you see here you have a hardware board. We are able to divide by the board size by 2 or 3, keeping the same functionality. And the last point concerns the extension of these AI capabilities to other platforms. The key point for us is to work on ultra-low power version, and I share the comment of our colleagues before. We must work on ultra-low power, which is a critical point. Second point, we have to bring more computing power, dedicated computing power. So we are going to add in the next microprocessor to introduce within 18 months from now, we are going to have a specific AI accelerator embedded in the STM32 MicroP platform. And also, the next iteration of advanced microcontroller will have also hardware accelerator. Those accelerators will provide far more capabilities in terms of AI application deployment. And of course, this will have to be done with the lowest possible power. So we have a roadmap enabling a new era of application based on AI. And this roadmap is going to be deployed with more features in order to address new application. Thank you.
Thank you, Claude. Claude, please. As you know, this is also business. And I am so glad that we have these very, very nice collaborations together in between MCD and Leti, and I wanted to celebrate it with this wafer. And once again, thank you so much for your trust and confidence.
Thank you. Thank you.
Merci en tout cas. Merci pour tout, c'était super.
Thank you.
Congratulations, gentlemen. Before we break for lunch, a few quick announcements. First of all, for those of you who have scheduled business meetings, make sure that you know that they're out in the business meetings canopy. Be there at the booked times, please. Second of all, make sure that you take time to take advantage of the Leti exhibition area. 45 exhibits. You've got lots of Leti partner and Leti products and demos. Also, buffet lunch today, sponsored by Applied Materials. Lunch is at 12:30, so you'll be pleased to know that you have a few minutes to network and make a few phone calls or whatever you need to do. Lunch, 12:30. Back here at 2:30 for the panel discussion on AI and ethics. I hope you've enjoyed the morning. Thank you for your participation, and bon appétit.